Yeah, so I propose that we begin the meeting. Hello and welcome everybody, and thank you for being here. Firstly, we are going to present our chapter and what we do, what we've done, what's the upcoming plans that we have. And then afterwards, we're going to give the floor to Professor Garmire so she can talk about her journey. So the floor is yours, Martin. If you could please share your screen with us, we can start.
Thank you, Arash. Just let me know if you can see my screen.
Yes. Yes.
Yes. Thank you. So good evening, everyone, and good morning to Professor Garmire in California. We are excited to see this wide participation in this event and to shortly present you with our chapter's main activities. This year is special for us because we celebrate the 15th anniversary of the first founded Optical Student Society here at the VUB, and this event seems to be the perfect occasion to commemorate that. It was in 2006 when the first meeting of SPIE VUB took place in an SPIE conference in Strasbourg. During the past month, we officially established the Elsa Society, and from then we are known as the B-PHOT Student Chapter, comprising both SPIE and Elsa, affiliated to the Brussels Photonic Research Group. As you can see, our kickoff meeting was held in slightly different conditions. To mark the start of this ambitious joint project between SPIE and Elsa VUB, we organized a competition to design a logo for our chapter. As it has already been announced on social media, we chose a logo with a pentagon shape, representing the connection between B-PHOT and B-PHOT Student Chapter with the colors on VUB, and the circle in the middle, including students, which represent the core of the student society, put in spotlight through the rays around them. During the past month, we launched several new activity formats, such as the very successful Professors Tell All, and this lecture series, faculty professors in photonics-related research areas speak informally about how they become who they are today, what were the main challenges, and tell us more about the academic life. Our own Professor Nathalie Vermeulen kicked off this series with an inspiring talk and a record audience. We started our new format discussion, the Photonics Club panel. Our brand new panel presented an introduction to the research conducted by different research groups within B-PHOT. The main theme of the event was conversational rather than strict and formal. Stay tuned. The next Photonic Club panel discussion is coming very soon. To give everyone an opportunity and a stage, we came up with Photonics, which is a series of webinars where you, as an active member of the Photonics family, can present chips. This was followed by the personal story of Yusuf about a 3-year interdisciplinary research project that he was involved in Iran. There are still several events we are excited and anxiously waiting to organize. B-PHOT Student Chapter is to host the Mon Plus International Mini Conference in June 3rd with the participation of 14 early stage researchers. Mon Plus is a European project with the goal of monitoring concentration of micro and nanoplastics in water and their presence, uptake and threats to animal and human life. We are also very happy and proud to have been awarded the SPIE AD activity grant for our upcoming event, Queer in Science, joining the VUB motto and celebration during the Belgian Pride with the motto, where the rain makes way for the sun, we proudly walk under the rainbow. For the celebration of the International Day of Light, we bring up the Idea Light event. This year, we are going to make a short video illustrating a simple phenomenon, including light in several languages, displaying the multilingual and multicultural character of our chapter. And of course, we continue our yearly traditions of the photo contest, who celebrates and acknowledges photography passionates. The topic of this year was Tell Us Your Light Stories Through Photography, and we challenge you to capture the beauty of light and its display in our daily life or in our cultural and social celebrations. And we have received many excellent photos. The winners of the photo contest 2021 will be announced by the end of this event. And now, lastly, I invite you to follow us in social media. Here you can directly find us in Facebook, but we also have an Instagram and Twitter account. As an important part of the chapter, we want to help you launch your career in these exciting and evolving disciplines. And if you want to be part of what I explained so far, don't forget to subscribe. We believe we offer a very good program for students working in optics and photonics. And please don't hesitate to contact any of the officers for questions regarding memberships. And especially if you have activity ideas you want to share with us, we can help you logistically and financially. We look forward to working with you, and thank you. I'll give the floor back to Arash because we are very anxiously waiting for the talk of our invited speakers.
Thank you so much, Martin. Just have an eye on the chat box as well. You can ask your questions there, and when we get to Q&A sessions, we can actually go over them. I'm just gonna give a short introduction to Professor Garmire's work and herself. It's my honor to introduce to you our first speaker, Professor Garmire, who's going to give us a talk with the title 60 Years of Photonics Research, Lessons from the Past and Projections for the Future. Professor Garmire is known for her tremendous and influential career. She has worked in optics, lasers, integrated optics, nonlinear optics, and so much more, and you'll pick them up from her talk. She's been at Harvard, MIT, Caltech, and more places where she contributed to the field. She has been the vice president and president of OSA, so she has a lot of stories to tell us about her experience in student societies and so on. She was the first woman to become an OSA honorary member, and she is the author of over 250 journal papers and holder of 9 patents. The list goes on and on. The list goes on and on, but I have to stop here so we can hear everything firsthand from Professor Garmire herself. Please, Professor, the floor is yours.
Thank you. Let's see, does somebody do this for me? Do I know what's happening to me?
What's happening?
Let's see. I guess I'm in the big view. All right, there we go. Now I'm in the view of myself, and I can look to see how I look and straighten it up and everything. I just wanted to say you forgot to mention the most important thing, which is that I've produced 30 PhD students, and I'm very proud of them. In fact, I've had people tell me how proud they are of helping a company make a lot of money, but I can say I produced 30 PhD students, and if we had the whole hour, I could spend telling you what each one is doing, and it's really fun to watch them as they get older. Let's see. Okay, and the other thing is, in terms of OSA, let me tell you that I can think of nothing more important than being involved in technical societies. I signed up when I was a student. They didn't have student chapters, but I signed up because, at least in those days, I had to have a membership to be able to read the articles. Now, I know you've got a lot of open access journals, but there's still many of the non-open access journals are among the best results out there. And but more importantly, that's how I signed up. But more importantly, going to meetings turned out to be incredibly important to me. The advantage I had is that I really did love meeting people, particularly the famous ones and the people that had written all the papers. And so I would pick out 3 or 4 of the best papers that I had read, and I would go to the meeting and I would look for the people that were authors on that paper. And usually there are 3 or 4 people. And so I would remember the names, and if I could, I would locate a badge that said on it who they were, and I would go up and introduce myself. Oh, I loved your paper, and you know, the formula you had I'd never seen before, or how did you measure that? And so everybody knew me, and it helped, because when I wanted to get jobs, I was a known quantity. Of course, it also helped that I was the only woman, but that's another story. But the reason to join is to meet people, to get inspired. I know that a lot of students go out there and meet only other students. I think it's important to have the self-confidence of the science you know. You know, when you're doing your thesis, you know more about it than anybody in the world, because you're doing a unique piece of work that you've concentrated on. So you have every right to be completely satisfied with the willingness to ask people questions. And that's really important for your career. The final thing that's really important for your career is that I had a profound thing to say. Oh, joining activities such as running this conference, and then eventually being part of the international activities in the US and elsewhere, is wonderful experience for when you're going to have jobs, because relating to other people, you know, you may be ending up working with people you don't like, and not having a boss to interact with. But if you can work out some of the crooks in your own personality by working on these groups in the society, you can make all your mistakes there. And I still remember when I was fresh out of my PhD being asked to be on a budget committee. I'd never looked at a budget in my life. It was tremendously valuable, and ultimately led me, after I was president of the Optical Society, to be asked to be the first woman dean of an engineering school. And all that experience came from societies like the Optical Society. So I totally support what you're doing. All right, at this point, I'm going to get rid of my face and hit. No, that's not it. My goodness, I've lost it already. Oh, there it is. There. All right, here's the talk. So I'm going to be talking about the beginnings of lasers. Now, I gather that none of you actually are focusing on lasers, but I'm sure that lasers are part of what you do, because everything you do involves coherent optics. And therefore, it's really important that you understand at least something about lasers. So this will tell you something about lasers. So let me see. I've done this as if I'm in Word, and I got to get used to doing it. All right. I'm going to tell you about stages in the development of technology, the early stages, both of lasers and of integrated optics. And then we'll talk a little bit about what's happening now. And the stages we're going to look at involve what I call prehistory. What happened before the invention? You always hear about the date something was invented, but it wasn't invented from what we call whole cloth. It was invented with a prehistory coming into it. That's why it wasn't invented before. It had to have that prehistory to get there. Then it gets developed and commercialized, and I'll talk about some of those. So let's begin with the laser. It had a prehistory like everything else, and that prehistory was the maser. Dr. Towns in 1963 made the first 53 made the first laser. He was my PhD thesis advisor, which is another story. I had never heard of him when he took me on. I'd never heard of the laser. I mean, it was only a year old. And so I was very lucky, not smart, when I ended up with him. Now, there was also a Ruby that already existed. It was in a maser predicted in 56. Oh my God, what's happening?
I think Professor Garmire's power ran out, her battery maybe. Hopefully she's going to be back soon. All right, I think at the same time, one of my colleagues is going to put some really interesting polls for you in the, I think, poll section of Zoom. So maybe, for instance, you guys can tell us about where you're from, what you do. Maybe even you can write it in the chat box, like, okay, what do you do, and like what department, what university you're from, where you're working. So that's going to be nice. Also, it's a really good platform to share your information, like from LinkedIn. I can see that Professor Garmire is back, but you can continue doing this in the chat box and the poll. Professor Garmire, I think you're still muted. That's all. Oh, all right.
Which way is it? It's, you can hear me now, right?
Yes, yes, yes. Yes, perfectly.
Yeah. All it shows is that this technology is not perfect.
No, it's far from it.
What I hadn't done is check to see that my computer was charging, and apparently it wasn't. I don't know how long it wasn't charging. Well, all right, yeah, it says 96% filled. Now you tell me why it said the battery had died. I'm afraid I'm going to have to get this place fixed, and that's not helping me. All right, so let's go back to the screen. Yes, thank you. Thank you, Bob. All right, get up there. There we go. All right, so do I get an extra 10 minutes? In May of 1960, he succeeded in making the first laser. And it was Ruby. Here's the Ruby in here, which already existed because it had been used in the Ruby maser. And he surrounded it with the flash lamps. And the result was that he used basically everything that existed off the shelf and succeeded in, the one thing he had to do is polish the ends of the Ruby. This was a cylinder, he had to polish the two ends. So this had a very simple design. So the lessons here, it was a simple design. It happened to be pulsed, it didn't run at CW. Because he had a flash lamp, it was a huge intensity and visible. The disadvantages were that it needed liquid nitrogen and had only a 4% efficiency. Now you're probably also gonna, is it flashing for you? I don't know.
No, it's not.
Okay, no. Good, because my computer is also not in good shape. and does some flashing. And this is a new computer. I'll tell you, I just cannot tell you how much I hate today's computers. The new ones, they're not designed for, what am I doing? Oh dear, they're not designed for people to do the old-fashioned work. And I had to go through it because Microsoft Word said it wouldn't keep the old ones. All right, back to the story. The question is, why wasn't Bell Labs first? Because Towns worked for Bell Labs. The answer is that they wanted CW lasers, and they were going to do that no matter what. And they had to do a whole lot of new technology to get the CW laser. So they weren't first. However, if you looked at the dates, they were less than a year later. They succeeded in getting a helium neon laser, which was actually a reasonable laser for quite a while because it gave room temperature and it operated CW, but it was only 3% efficiency. The guy that got, in fact, the second laser built, he just completely copied Maimon's design and just put uranium and calcium fluoride, and total dead end, waste of time, waste of everything. You have to have a good idea of why you're doing what you're doing to really make a difference. Otherwise, it's a dead end. So I list in 1961, just a year later, neodymium in glass. Now that didn't take off for a while, even though it was room temperature CW and a lamp pump and very efficient. It was in the infrared, and for the pump, this was a pumped laser, lamp pumped, and the Bell Labs wasn't impressed. And so it didn't go very well because Bell Labs was doing most of the research. But it has become very important, and it is, for example, the laser that they use at Livermore in the United States to do laser fusion with. So it can scale up to megajoules in pulses. The gallium arsenide diode, I'll come back to. The 2 years later, there was the ionized argon laser. It was important for a long time. It was a gas discharge laser, but it worked on an ionized atom. It was very, very inefficient, but it put out huge watts of blue and UV. It became important in laser light shows. That's another story, but I started the first laser light show with an argon laser. The argon laser is gone now because that's not true. Well, a lot of it can be done by second harmonic generation of neodymium YAG, which was also invented the same year. And this is a very important laser used for many things. I also include the carbon dioxide laser, which was very, very efficient, but it was 10 microns, which basically means all it would do is heat things. It's used for many machining applications. And then organic dyes, which were very important for 20 years. They were a liquid that had dye in it. They were optically pumped by another laser, and they were broadly tunable, and they allowed for very, very broad lasers, line widths that ended up being mode locked and were the first pulses to get under a picosecond in time. So they were extremely important at that time. But how many years later that is, 20-some years, little less. The Ti-sapphire laser was invented. That's titanium doping sapphire. And it was the first solid state wideband crystal laser. And it ended up displacing most of the dye lasers because it put out femtosecond, the shortest pulses in optical pulses in history, attoseconds now. And the Moulton, who did this, also went ahead and formed a successful company. The message here is that just because you've got all these wonderful things, don't quit looking. And if you think outside the band, which outside the box, which he did, he thought outside the band and made a revolutionary changes, which actually this laser led to the Nobel Prize laser this past year, or 2 years ago, that my good friend won. The woman. I'm sure you know her, all you women. I knew I'd forget her name, but I've known her.
Donna Strickland?
Yes, yes. Now, since way back, I've known her, and it just really embarrasses me. I keep forgetting her name. Anyway, quantum electronics as a new field was new at that time. And the concept was that you took electronics, which is a well-known subject, and quantum mechanics, which is a well-known subject, and you brought them together. You cannot understand a laser without knowing something about electronics and quantum mechanics. It's the same thing trying to understand a semiconductor and semiconductor devices. You need to know about quantum wells, and you need to know about electronics, PN junctions. So anyway, what are the lessons learned here? That mixing off-the-shelf items is the way to win the race. That's why Maimon beat everyone else. He took an ordinary flash lamp, ordinary ruby, polished it into silver ends, and dewars were already invented, so he can go low temperatures. The next lesson is that all important lasers were found in the first 6 years, except for the Thai sapphire. And the important thing there is, first of all, everybody jumped on it as soon as it came in, and they tried their ideas. And the ones that won out were the ones that were easiest, most robust, turned out to be the cheapest. You know, all the reasons why you like these lasers were present and why they were so easy to make. Put another way, all the hard ones ended up not being useful for various reasons. So one of the things that you guys are facing is a whole vast array of technologies. Which are you going to use for what you want to do? And the message is, you don't know, but somehow or other, look for the easiest if you possibly can, the most well-behaved, etc. Now, after having done these first 6 years, the taming of the laser took a long, long time. Because the laser is highly nonlinear due to its threshold, and it was necessary to understand and control all its nonlinearities. And an important part of that then for the invention of the useful lasers was computer control, which was required to really optimize performance. And if you're working on some integrated photonics of various sorts, that computer control is likely to be an important part of what you do. So you're probably going to need to either learn computers yourself or have somebody in your group who can do all the computer design to go with whatever you're trying to build. So we're now into the development stage and talking about, in fact, photonics. How do you design photonics devices or systems? The first question is, what do you want to do? Yeah, you've got to decide what you want to do and the constraints to what you want to do before you even begin. And having once decided that, then you realize that photonics are a very complex technology. There's just many pieces. And so you really need to think of systems design. And if you're a physicist and want to stay in this field, you should go take a course on what they do in engineering. Take a design course, because I learned all this when I became Dean of Engineering at Dartmouth, and they teach a very good course in systems design, because what you need to do is take your system, whatever it is, and divide it into its separate parts. And then you can check, is each part available? What part needs more work? So you've got to focus on what it is you're going to do. You can't just listen to what your professor tells you to do, or the higher level student or the postdoc. So let's just pretend we want to integrate a laser into photonics. We've already talked about lasers, so the initial system design we know is going to be an active medium. So for our integration purposes, we're going to take semiconductor lasers. And then other things in the semiconductors might be electro-optics. We could use the semiconductor in a monolithic way, or we could make up hybrid combinations. We also have to introduce a way to pump it, which was going to be electrical. So we have to look at connections and the packaging of all of that. And then ultimately, for a laser, we need a cavity. So we need to imagine that we somehow can put mirrors on this thing. So, all right, we know what we're going to do. We know what materials we're going to do. How do we build it? Now that's, of course, where a lot of the trouble is these days, or I should say the research is days. How are you going to build this? If you go to 2D materials, you unpeel them off a substrate and put them somewhere else. So there's processing. Then how do you integrate it in with everything else? And ultimately, how do you package it? And I'll just show you examples of how this happens for semiconductor lasers. What pump mechanism are you going to do? Is in your case, it's probably electrical. It could be a laser. It could also be a MEMS, which I didn't write down here. So that there are mechanical ways for some of the things I see that you want to do. Environmental constraints, is it all right to work at low temperature? Do you want it at room temperature? Maybe it has to go at high temperatures. How long do you want it to last? If it's going to be used once, maybe a few milliseconds, who knows what it is. Efficiency, generally speaking, you want it the most efficient possible, but usually that matters. Now, as far as lasers are concerned, the operational specifications will be things like the divergence of the beam. Are you going to run at CW, or is it going to be pulsed? And if it's pulsed, what kind of pulses? Fast, slow? What frequency is it going to operate at if it's pulsed? And what line width is it going to have? What wavelength and what line width? And then there are extraneous requirements that we teach at Dartmouth, such things as cost. Is it going to be expensive, or is it going to be something that's cheap and could be sent to third world countries? Is it rugged and durable? Is it what I call idiot proof? In other words, can somebody who is not knowing what they're doing, can they still make it work? Is it just a switch to turn on and off? Some people like to buy elegant things, and we always add legal, because there are certain things that are not legal, one of which is an exact copy of something that's patented. And that may mean that you have to try to find something new to make it not an already patented item. So I'm going to look at the example of the first diode laser. And the prehistory I keep talking about in this case was looking at gallium arsenide at low temperatures. They had a little piece of, it had been diffused to be a PN junction. The gallium arsenide was this slab here, and they looked at electroluminescence. In other words, they put on a DC contact. It wasn't DC, it was microsecond pulses. They're contacted with an indium zinc sphere that allowed them electrode, and they had a PN junction, and then they looked out the bottom by putting this whole thing on a molybdenum ring. The details matter if you've ever done anything but in 77 degrees Kelvin, which I have. It's very hard to build something in that structure, in that container. So the theoretical requirements for a laser are that the quasi-Fermi levels, their energy separation has to be greater than the photon energy. Now, if you don't know solid state physics, all that really means is that PN junction will enable gain. And that means that the stimulated emission gain is greater than the loss. There are no other loss processes for the electrons. And finally, the cavity has to, the optical cavity has to contain the active region. And then you'll have the resonance at the wavelength you need. Everybody knew this at that day because of the paper by Towns, which had happened 5 years earlier or so. So there was a race to demonstrate the first diode lasers. And again, this happened very rapidly, within 6 months. General Electric, IBM, and Lincoln Labs all succeeded in making the first laser diodes. How? By basically copying everything that was done in the previous paper, much like happened with the original laser. With GE, they took a very tiny microcube. It was too much trouble to draw it here, but I showing you a PN junction, and they diffused a transition region, the zinc transition region, all the way through, so that the junction was going across here, and the light was coming out along through that diffused layer. And as they pointed out, it was the first laser involving transitions between energy bands. Now that's also a new concept, because it had only been atomic levels before for lasers. So this was fundamentally different, but the experiments basically were identical. And I won't go through the details. They polished mirrors on the cube to get their reflectors, and they spoke, and they wrote coherent infrared radiation from forward diodes PN junctions. The message in all this is the word coherent. Coherent meaning that it was like a laser, so it was truly stimulated emission. And the proof was it was sharply beamed. It had a threshold current after which the beam increased abruptly, and it had a very narrow spectral distribution. Within a month, IBM copied and had the same thing. In fact, they copied exactly what Lincoln Labs had done, this drawing here, and showed the line would narrowed. And importantly, they pointed out that with the efficiencies they found, if they had greater currents, they would have gotten to a quantum efficiency approaching 1. In other words, for every electron hole pair that got recombined, you got a photon. And that was absolutely remarkable. Nothing in the world could do that. So this was very exciting to people. And MIT finally got its work published 1 month later. And it specifically actually took data more than the other papers, all the way down at 4 degrees Kelvin, just to prove this was a really physical device. There's the threshold, the current. This is a log plot. If you want to see an amazing plot it log. This is over 3 orders of magnitude in temperature and 4 orders of magnitude in light out. And they still saw an incredible threshold down at low temperatures. At liquid nitrogen temperatures, yes, it was there, not quite as badly, but it lets you know that you have a real potential to do something incredible. At liquid helium temperatures, this shows the natural line width of the gallium arsenide, very broad. This is 400 nanometers, I think. And the above threshold, it became very, very narrow, again, which was predicted by lasers. So what did we learn from going through these details? Well, again, the initial system designs all used the prehistory setup. So of course it only took 6 months. They already had the material, the structure, the pump, the environment, detection method. All they had to do is figure out how to put on mirrors. And basically it took 6 months to figure out how to polish the faces on these small guys to make mirrors. And eventually cleaving turned out to be much better. The original guys could have done it if they had known about cleaving. Anyway, actually, they didn't know it because they didn't really know about lasers. The other people all had somebody in their group who actually knew about lasers and the importance of mirrors. So the lessons learned: stay up to date on new science and technology. You really have to do that. Don't rely on your professor to do it. If you can get a new idea, your professor will love it. Copy as much of the previous system as legal, i.e. that it's generic, it's fairly obvious. And then you can define the improvement that's going to make it better, because there were still serious limitations. Who wants to operate at 77 degrees Kelvin and on short pulses, all because it was getting too high a threshold? It was also infrared. Wouldn't it be nice to turn it into visible? So you want to improve the laser? The first thing you have to do, or improve your device, the first thing you have to do is, what do you want to do first? And obviously operate at room temperature. Nobody is going to buy, I mean, the computer people are always thinking about this. They have optical computers that work at liquid helium temperatures. But who's going to buy something that somehow has to have liquid helium? So you need to operate at room temperature. How do you do that? Well, you have to increase the gain. Well, how do you do that? That's not all that easy. You can increase the gain by taking down the 4 degrees Kelvin, but as you get up to room temperature, you lose gain. So you have to decrease the losses. It's all in the losses. It's all in the losses. So you have to keep the carriers, the electrons and holes, in their active region. How are you going to do this? There's no method at that point. So we need to have a new structure that will work, basically coming up with new materials, and also then a new way to fabricate the structure. So in 1963, the heterostructure laser was developed as a concept simultaneously by Alvarov in the Soviet Union and Kramer in Varian in the USA, a company. And this concept won them both the Nobel Prize in 2000. It was that important because it was also the concept that led to white light LEDs, and that was part of the whole package. The idea is that these boundaries will allow electrons to flow this way from the outside in, and then the holes will come this way, and these barriers will keep them there. And so this region here collects electrons and holes and doesn't let them leave. So, quote, this was in the paper, "Great benefit can be derived from potential barriers at heterojunctions." 1963, remember that date. In order to happen, they had to be able to grow this thing. It's easy for a theoretician to say, wouldn't it be nice? But to actually make it, you guys, I'm sure, know the making is where all the challenge is. So they needed a more efficient way to fabricate laser diodes than what they'd done so far. And the only technology available at that time was called liquid phase epitaxy. And I tell you this because I built the first liquid phase epitaxial system in a university laboratory. These had all been developed in companies. RCA had done it to grow only gallium arsenide. And it turned out that what you needed to grow this heterostructure, you needed some gallium aluminum arsenide. Now, there were other ways to grow gallium arsenide on gallium arsenide. Mostly vapor phase epitaxy worked very well, but that failed with aluminum. It just absolutely didn't work. They tried and tried and tried. It took 6 years for the LPE to finally happen. And that was in 1969 when it was actually first done in a single heterostructure, which didn't work CW. And then in the same year by Alferov in Russia, went ahead and built the double heterostructure laser, which is this structure that had the wide band gap materials, the gallium aluminum arsenide on both sides, and had a narrow region here which controlled the electrons and holes very well. They're drawn here with little pictures. And this actually worked at room temperature, and it had a threshold, so it was a laser. When pulsed, the threshold was 10 kiloamps per square centimeter. That's a pretty high threshold if you know anything about it. Within a year, Bell Labs had the same double heterostructures working, but at a 5 times lower threshold. Get rid of that S. And they published a picture showing the actual light coming out of the laser diode, which they could now do because it was at room temperature. So that wasn't good enough. They were still pulsed. They didn't run CW. What had to happen? What had to happen is that the device geometry had to be improved. And when the device geometry was improved, you had better cooling and packaging. So the stripe geometry was, as it said, they made a stripe across there are these mirrors on both ends that are formed by cleaving now. And the stripe geometry was 10 microns wide and confined the current to only that very small area. And that increased the efficiency tremendously. They then mounted it on a diamond heat sink that was as good as they could get, and very carefully put everything together in an integrated package. And so this was the first formal packaging that was done. And they got thresholds down more like 6 kiloamps per square centimeter, and it worked up to 180 degrees Fahrenheit. So they got rid of all the waste heat and the waste electrons, but they still had a high threshold. And their reason was that there was still some spreading out of the current under the stripe until the Mesa stripe geometry was invented, which was in another 2 years. This was in Japan from Hitachi, and they ended up with a CW laser with a threshold of 75 milliamps, which at that time was the first time it was done. Actually, they're now down at microamps and below, depending on the size. But why were there no commercial lasers then? What time was that? 72. Why were there no commercial lasers? And the reason was that even by 1970, everything they made showed a gradual degradation with time. In 1976, I was in a company that worked with these lasers and found out that it was 4 hours of operation CW before they died. You can't exactly sell a laser like that. It took 8 years to explain exactly what was going on. There was an increase of recombination centers. I won't go into the details. There were other issues like catastrophic damage. If you put too much current in, you had to control the current. Facet damage, the facets with the mirrors eroded, and there were thermal runaway if you ran it too hot. So the solution to all of these problems, which were desperately serious, were that you had to be careful with how you fabricated them. You had the material changed, composition turned out to be made less sensitive to these problems. They coated the mirror facets, they altered designs, so everything had to be handled to solve these problems. And they did, and the first commercial grade lasers were 1984. That lasted a long time, 10,000 hours. That's a lot of years. I don't know how many years that is. These operated CW at room temperature, 850 nanometers. It took 20 years to reach that point. And my point to you guys working in photonics is I predict it's going to take 20 years for a great deal of the things you're working on to want to become practical. I'll be a little nicer and tell you maybe 10 years, because the technology is not as simple as it was in those days. You have a lot more things to work with, but don't expect them to make you millionaires within 5 years. That's my prediction. But finally, they were improved well enough by 1982 that they can make CD players. And in 1985, the Sony Walkman came along. Now that date is before you guys were born. Have any of you heard old-fashioned records? I'm sure you've heard them for some historical reason. The first time I picked up a Walkman in 1985 from the store, it blew my mind. Amateur musician, my sister is a professional musician, played the cello for the Cleveland Symphony, and I just couldn't believe it. It was night and day. She said they had to buy all new chairs because now they couldn't have any creaking of chairs when they were making records. It just, you don't know what difference that CD player played. And I was so proud of lasers. The lasers were finally being used for something useful. Now, the reality is there's another whole story in telecommunications with a whole different group of people. But I realize you don't know anything about it. You just pick up the telephone and then use it. So anyway, what they really wanted, though, was barcode readers, laser printers, these things you've seen. They all required red lasers. You needed to be able to see them. And also for laser printers, you had to have high energy photons so that you could imprint onto the photoconductive platinum, which is the way they work. But efforts to grow double heterostructure lasers failed. Apparently there were no available direct band semiconductors, and there really aren't still today. But in 1985, I mentioned the quantum wells were invented in 75, but in 85, they discovered that they increased the photon bound gap, pushing it all the way into the red, and they were able to make the first laser printers. And as an outgrowth of that, low-cost red laser diode pointers became available. The story to me there is, if I were there in person, I'd hold up the red laser pointer and say, do you think all this research was done for laser pointers? The answer, no. You're not going to make any money if you're buying a laser pointer for $10 or somebody's selling it for that. You really need a massive, expensive product, and you've heard me talk about them. There are different wavelengths, of course, were needed. As I say, Bell Labs had a whole set of, the Bell telephone system works on a whole set of wavelengths different when we discussed. And they invented the quantum well lasers partly to be able to reach these other wavelengths. And you probably know about quantum wells. If you put electrons into a very thin layer, they fill up that layer and they have very discrete energy levels. And that ends up to lowering the threshold considerably from that quantization fact. But they needed then to fabricate new layers that were only 100 microns thick. And that was not easy. They needed new materials of 4 layers. LPE was outclassed. They couldn't use it anymore. And they succeeded with 2 new technologies, using metal organics for the vapor phase or molecular beam epitaxy. And those 2 technologies with other names in other places are basically still doing the job of any layered structures you need in semiconductors. Other things were done. 5 layers, 5 different materials were incorporated. They can do magic these days. I've got to tell you, the happiest laser diodes are indium gallium arsenide on gallium arsenide, which is going to strain the quantum wells. And nobody thought it would work, and they didn't do it until late. But in fact, they're better than any other laser. And if you ever need a wavelength, the best lasers are at 980 nanometers in the near infrared. And by 1996, they were able to get 8 watts out of such a laser at room temperature with CW. So I once predicted they're never going to make a laser of even 1 watt. So I was way off. There are more important breakthroughs, but I'll pass them. Quantum dot lasers, quantum cascade lasers, those are the 2 totally different kinds of lasers. And the holy grail was the blue UV diode lasers. And they led to a Nobel Prize in, I guess I misplaced putting it, sometime fairly recently, at least in my lifetime, your lifetime. Anyway, white light LEDs, I'm going to skip all that because I want to get to the first thing is Richard Feynman wrote a talk, and if you want to be inspired or depressed, go to read what he said in 1960. There's plenty of the room at the bottom. And this is basically what I see ahead. There's plenty of the room at the bottom. He said, he began his talk with, there's a staggering small world below. He said it could be reached by the year 2000. Well, obviously it wasn't. With electron microscopes or ion beams, they had in principle the ability. So he predicted trying to write data digitally, which means he predicted the CD player, and you could put on 6 or 7 bits of information per level, per dot. That predicted ASCII. And he postulates that if you made the dots as small as 800 atoms, you could put 24 volumes of the encyclopedia on 1 pinhead. And of course, in those days, everybody laughed at him. I won't get into the details of how we laughed, but we did. He predicted DVDs. There must be some coding material that would record the pattern, he said. And he even talked about volume storage. If each dot was a cluster of 125 million atoms, all the books in the world could be written on a cube of material 1/10 of a millimeter on a side. That's 100 microns. But of course, how would you read it? And he thought, well, you could read it through an electron microscope somehow or other. By the way, I checked just for fun and found out that there's 9 times as many books available today as in 1960. 500 million, I guess. So he actually predicted computers. He realized the DNA could be a mechanism for storage. We're talking about that today for data storage. But he also read that biology does not simply write information, it also does something about it. So why not make smaller computers? How small a thing can be molded, he asked. 2 microns? You guys know it can be a lot better than that today. In such small machines, the strength of materials is very much greater. On the other hand, the grain structure of materials means material is not homogeneous. All of these things are things that you get to face with what you're doing now in nanotechnology. Can we arrange atoms the way we want, all the way down? What would happen? Layered structures with just the right layers? That, of course, is the 2D layers that they're working on now. New properties of materials if we could really arrange the atoms the way we want. Wouldn't this satisfy every need? 80 years ago, he predicted nanotechnology. So that's my lead into talking about integrated optics. So I'm taking you all the way back to 1975, and we didn't know what we were doing. We had the general idea, and these are recent pictures off the web of what integrated optics might be to different people. I'm not going to go through it, We, of course, called them integrated optical circuits, IOCs. But of course, they had to come up with a new name because it was a new technology, and I'll show you why it took a while. They were called photonic integrated circuits, which is what you guys use as a name now. Never mind. So we define integrated optics as integrating at least two functions on an optical chip. We started with optical waveguides and planar substrates. Now, of course, there's 3D of functions. And to me, I think that's really important. I didn't put that in red, but I should have. Thinking outside you've heard of thinking outside the box. This is thinking outside the plane. A lot's happening in that area, and I think it's got a huge potential. I won't bother with prehistory. In 1969, there was something called Introduction to Integrate Optics. Stu Miller at Bell Labs gave a talk that said this is a new exciting thing to be. The prehistory merely says that others had already thought about it. But he pointed out, of course, that the refractive index changes can guide laser beam in widths of 10 microns. So he was thinking of the dimensions UR and smaller. And he mentions photolithography, of course, makes this possible. So in 1970, I should say that I got my PhD in 65. I went to stayed at MIT for a year. And in 1966, came to Caltech to work with Yarif. And so he was paying attention and he heard about this work. And so while others were trying to grow films like sputtered zinc oxide, etc., we were already working in gallium arsenide. And he had already seen that PN junctions made waveguides. So he built I'll say, because I had a lot to do with it, the first electro-optic modulator in gallium arsenide. And I built the Schottky barrier. That's what gave the electric field. 100-volt Schottky barrier. That's in reverse bias. It had never been done before. That's the value of working in a place like Caltech. And a few other things were done. I will mention the first distributed feedback laser by putting dye and gelatin and embossing the grating. That was done at Bell Labs also. And then ion implanted gallium arsenide as a waveguide was also my invention. It lasted a while, but it got superseded by a lot of other things. So the early research involved a bunch of materials, and I won't go through this. I'll merely say that by 1975, it was quoted, integrated optics draws upon many other disciplines, microwave and integrated circuit technologies, solid state physics, optics. There are new devices, materials, and fabrication techniques. The reason I'm telling you this is, again, you need to have a wide understanding of a whole lot of different things if you want to have the full vocabulary with which to think about new ideas. However, in 1975, there were still many problems, including no simple and efficient way to couple to optical fibers and thin film devices. I don't think that's solved yet. By 1980, they admitted there were few functions integrated, only a single device with promise for integration. We were, however, very excited by advances in semiconductor lasers because they were working. The research was basically dead. So I just want to say a couple more things. One is the rate of research progress. I couldn't resist this. I like to look at the Science Citation Index to see how fields are developing. And you can see that integrated optics was pretty exciting at the beginning for a few of us anyway. Then basically nothing happened. And by 1990, everything started to grow. And in this area, this was the first time that integrated optics in gallium arsenide devices really became practical to think about. And then if you look at your field, which is integrated photonics, I've taken it from 2000 to now, that's 20 years. It's this basic growth that we're seeing. And I'm telling you this because you're in a very exciting field. It's still growing, maybe not quite as rapidly as at the beginning, but it's growing. I think that it's getting a little harder to do some of the more sophisticated things, but the citations to your papers are also growing incredibly well, which means that you're getting 6,000 publications a year are citing your papers. And that means this is a very active field, and that's what I'm trying to say. So what have we learned? We've learned that integrated optics is old, but it never was successful because it was completely dominated by material and fabrication difficulties. Those are the subjects you have to worry about. And the funding disappeared because it wasn't practical. So many advancements were required. The technology improvements in the last 20 years that are helping you out are things like ion beam technology, tools for IC fabrication, MEMS. They were all adapted for your devices. Microscope technology is vastly superior. Microfabrication, nanofabrication, etching, cleaning, measurements, observations are so robust and work on many materials. I could give my eye teeth for those. The photonic crystals, metasurfaces, nanoplasmatic structures, the 1D graphene-like structures, all are available, and device modeling software is available. This is a picture I just picked up off of the web because this shows even our devices were this size compared to the Fabry Pro modulators that you now can build doing this. So as Feynman predicted, size is everything. And it's a very important part. And I couldn't resist saying by 2012, we didn't make it by 20, but by 2012, the single atom transistor took a single atom and made a transistor out of it. It built the devices with atomic precision by combining scanning tunneling microscope and hydrogen resist lithography. It put a single phosphorus dopant atom into an epitaxial silicon device. Granted, it was at 4 degrees Kelvin. If you want to do it, you can do it. The question is, how do you get those up to room temperature? And I've just written a few other examples to show you that I know something about it. So my conclusion is that nanotechnology is taking over. Feynman was right. Fundamentally different materials will replace the more traditional ones, and I'm sure you're already doing that. You don't need me to tell you. Nanostructures embedded in nanoparticles embedded in things. So I've written a few other things in creative geometries. Nanotechnology will include micro or nanospheres and other resonant structures in all kinds of 3D arrangements. Theoretical analysis will require exact solutions to electromagnetic waves when nanostructures are less than a wavelength. And symmetry breaking, metasurfaces, single atom thicknesses, they're so exciting. Continued improvement of fabrication technologies, integration technology, etc., are all required. Ultimately, packaging and testing for reliability is crucial. Low cost, low cost, low cost. So ultimately, creative and dependable out-of-box thinking is your most valuable asset. And that's my talk. If you want to contact me, my name is easy to remember, and it's just at Dartmouth. I am retired, but I kept my phone there. So I'm open for questions, and I should say, if you want me to answer any questions about how I got all this done in a finite life, I can answer that too. Because I have two wonderful children who now have their own grandchildren. I have I had another whole life as a artist. I started a laser light show called Laserium, which you can read about on the web if you care. And I've discovered that the Smithsonian wants my papers on art in their collection. They don't care about my science papers, but they like my art papers. So, questions?
Thank you so much, Professor Garmire. We have a lot of questions in the chat box, but I'm going to go to Professor Thienpont in the beginning to see if he has any questions for you. Professor Thienpont?
That's very nice of you, but I think the students should have the privilege to talk to a fantastic icon like Professor Garmire. I think it's just a privilege. It's a great honor to have her with us tonight. I've always looked up to her. She was a fantastic role model. I listened to her presentations at a lot of conferences. I looked up at her when she was general chair of nonlinear optics conferences. So I'm not going to waste your precious time, dear students. Please take this opportunity to ask that wonderful lady all the questions you want.
I have to answer that, just to tell you that you looked up to me because I'm 6'2". I don't know what that is in centimeters, but it's high.
Oh my God.
I always got noticed. That's another thing that, I'm sorry, I have to interrupt. For women, women would say to me, well, of course they notice you because you're so tall. But I had a very good friend who was 5'2", who was noticed everywhere she went too, because she stood tall and straight, and she was willing to walk right up to people and talk to them. And she didn't have any of those sort of old-fashioned feminist characteristics. She wore lots of jewelry and was very beautiful, but she was assertive, and that's all you need.
Amazing. Now. So I'm just going to go to the chat box and give people priority how they wrote in the chat box. So Tata Victorian is asking Professor Garmire, what was your personal feeling about the lasers in 1960?
I had a choice to do a PhD in with the helium neon laser or the ruby laser. And I chose the ruby laser because I could see it and the light was pretty. I discovered I really do have a very basic love of how things look. So laser light, absolutely, even to this day, it just sends me into heaven.
And did you expect all the revolutions that came with lasers?
Oh, of course
in the
not.
Beginning.
Oh, I was a student of Towns, and he understood the importance of optical. Understand, I'll be late. They know that. Excuse me, I have another meeting, but I'll put that off. What was your question again?
So did you actually in the beginning expect that all these revolutions would happen?
Right. Dr. Towns knew that there was a desperate need for lasers for optical communications. And he understood and predicted that the world would be able to communicate with optics. They had reached an absolute limit to what they could do with microwaves. They were running microwaves across the country to try to communicate, and every time it rained, it would die, and microwaves couldn't go into tubes under the ground. So fiber optics was desperate. So we knew that. What was a surprise, total surprise, was the ruby laser. Nobody knew that it was going to be able to blow holes in razor blades. And the first time you got a ruby laser working, since I wasn't the first, I knew that I had to focus it down and see if it was powerful enough to blow a hole in a razor blade. And if it didn't, I had to go back and realign it. So from that time, we knew machining was also important. But if you look at the concepts, what's been done, is just no way you could predict it. I was on a committee that got a chance to suggest that LIGO be built. And LIGO, of course, has measured the collision between two black holes. That all relies on a laser. That's the fundamental technology it uses. We couldn't predict that, etc. Yes.
So the next question is from Carlos Diaz. Did the first laser receive a patent since the other ones were made in such a close time to it? I think it could have been a competence for those rights. Competition, I think it meant.
There was definitely competition in a very serious way, but it really wasn't the patent because Bell Labs did not believe Maimon's result. They just couldn't believe it. And his paper was sent to them to review, and they rejected it. They said it should not be published. And he had had only very preliminary results. And I mean, he was a PhD from Stanford or Berkeley. He was definitely well known, but they just didn't believe him. And they were desperate at Bell Labs to be first. And so his company said, we want to be first, so send it to Nature. So Nature published it just as it was, and it got out ahead of time. And I've looked at the paper. It really is a marginal paper. I'm not sure I would have believed it, but he was right. And so he didn't win any Nobel Prizes. He didn't even win any prizes. And he was ostracized from the community for a very long time. And it was Japan that decided he should really get a prize. And they had some kind of a Japan prize that he gave him. And then the Americans started saying, oh, why aren't we looking at this guy? He had dropped out to start a company in lasers after he got it to work. So he wanted to make his name in a company, want to make a lot of money. And he failed in that. I could go on to the story. I've had dinner with him, I know. But you have other questions.
Yeah, so Martin Iskenderas is asking, what is your creative process? You've been all around with a lot of creative ideas. What's the process behind them? How do you come up with new ideas?
Well, as I said, you really have to be there early. You really have to be thinking. I'm not as sure that I've been as creative as you think. I've had a lot of creative students. But one time when I really was creative was in optical bistability. It had been invented as a nonlinear material put between two mirrors. And I said to myself when I read that, well, what if I made an artificial, somebody had invented an artificial material by putting electro-optic, I won't go through the details, but they'd made a very specific, a nonlinear fabric pro they'd made, and they made it artificial. They they used a detector and they fed it back to the signal across the electronic signal. And I looked at it and I realized there was nothing special about it being a fabric pro. And so I wrote the first really paper that said, anything you take and put feedback on can become bistable. And that was followed by a whole bunch of examples made by a lot of people in a lot of different materials. We demonstrated it just with electro-optic modulator without a fabric pro. it was also bistable. And so that took a sort of generalization of something somebody had done. And I think generalizations, going to new materials, going to anything you can generalize it, is the way to be creative.
Amazing answer. Yusuf, do you want to actually, I see your hand is raised. Do you want to actually ask your question yourself?
Oh, yes, I forgot to put it down, actually. Well, now that I'm on it, why not? Why not to make your job a bit easier? My question was about, what do you think is the next big thing in photonics, which can, I know there's a lot of next big things, but something that's be compared to the laser technology, which revolutionizes everything. Do you think it will be something like biophotonics, putting photonics into body, or quantum computing, putting lasers in our computers? What do you think is the next big thing?
Well, I've proven I'm no expert in being successful on that, since I didn't predict. I once said they'd never sell a laser for under $1,000, and that was in 1975 dollars. So I missed out on, because in those days the laser diodes all cost that much because they were used in telecommunication systems and had to be ultra durable and reliable. And I didn't understand the economy of scale. Anything you can make cheap, like a laser pointer. In fact, I will give you a story. People talk about a green laser pointer, right? Do you think there's a green laser inside? Answer, no.
No. Really.
There's an infrared invisible neodymium YAG laser, just as I said that was important laser. This little laser is only about 100 microns across, and it's a laser. So they take an infrared laser diode, they send it through a neodymium, very small crystal. That makes a very sharp line in frequency space, in optical frequencies. They send that through a second harmonic crystal. There's where my nonlinear optics comes in. And it's doubled into the green. And if you look at a drawing of that, and you can find them drawings on the web, they're extraordinarily complex. They're just amazingly complex. But if you can make 1 million of them with automated machining tools, you can sell them for $30.
So you think economy defines it more than
Oh,
more?
absolutely, absolutely. And need. I mean, I think those aerators for the body are hugely cheap now because of COVID. I mean, you just need a market.
True that.
Yeah.
Thank you very much.
Olga, I also see your hand raised. Can you please ask your question?
Yes, but I have a question. Thank you, Professor Garmire, for the nice presentation. I have a question out of topic a bit. I wanted to ask you about your story. You know how now we do this women in academia, this 50-50 equality. What was your story about this, that you're a woman in physics working among men?
Well, in my day, there were none. I mean, I was a graduate student at MIT in physics, and I never once saw another woman graduate student. So it was a do-it-yourself. Now, my advice is stick around with other women, because you will have a whole series. You are different from men. I'm sorry to tell you that, but I think you are. And you will have a number of challenges or excitement, opportunities very different from men. You know, the obvious one is family and children. Now, there are plenty of people that are successful, and you can talk to Nobel Prize winner, whose name I keep forgetting, and who has a very helpful husband. And I know many people whose husbands have, well, my own husband is a second husband, but he has decided that I come first. And there's nothing more wonderful than having a spouse, it can be any spouse, that thinks your work is more important than theirs. Two people that are equally important does happen, Margaret Murnane and Henry Captain are married and have been since they were in graduate school, and they're equally famous. And they work together all the time. So everything is possible, but being conscious of it is the important thing. In 1970s, when all this other stuff was happening, I also went through the women's movement, and we had what was called consciousness raising. We don't really use the term anymore, it's hard to say, but we met in groups of 10, 12 women only and talked about our issues and came to realize that a lot of them were really due to the politics of the situation. And I think men have changed a lot, so I couldn't possibly tell you what to do in your present situation, but be proud of what has happened, because back then there was a whole bunch of men that tried to keep their positions on top, and that is much, much less true now. So it is still there in some areas, and engineering still tends to be a male-dominated, pretty male-dominated, but get involved in the women's organizations. Society of Women Engineers is the one in America, and you will do fine. I think it helps in getting tenure. There are a whole lot of things that have been written or said. I have, if you put my name on the web, it is a unique name, fortunately. I will say it's the name of my ex-husband, but along with Elsa, it makes it unique. And I've been interviewed before on a variety of topics, and you may find more answers there.
Thank you very much for your answer.
Last question, and then maybe later on other people can ask their questions in the networking session or through your email. Ashley Cholian is asking, what was the role of optical societies in 1960? How did they help you in your career?
I was extraordinarily lucky because actually in 1960, it was almost totally male. There was a woman, the woman that ran it was female, but she wasn't really a scientist. But very soon, about 65, yeah, 66, absolutely wonderful man took it over called Doris Quinn. And he was absolutely convinced he needed women in the field. There were two famous women who had been in optics, perhaps married to another one who was in optics, but there were a couple of women that had done anything, but there were no women in the society that I knew when I started. But he right away got me involved, and within a few weeks, I was asked to be on committees, and that helped me a lot. So during this whole time frame, there were both people that helped a lot. Being a woman helped a lot. I was visible, but they were hindered as well, and I can't really tell you which was more important than the other. I will say, oh, I guess I didn't mention it, but I will say there are several times in my life when I almost dropped out, starting the first year of graduate school, when I was absolutely miserable. They had put me with the wrong person, and I was just miserable. I went home every night and becoming a secretary, which is all that was available for women then. But I stuck it out. And another time when I was a postdoc, I felt like I was just not getting anywhere. And that's when I took up this art field. But then after that, and I lost my self-confidence, but I gained it back through forcing myself to, I decided it was safer to be a scientist than an artist. There were a lot more money available in science than in art. I mean, literally, that's how I made this decision. So you don't have to be absolutely passionate about the science. I didn't start out passionate about the science. I became passionate because I got interested. Sometimes I imagine, what if I had gone into marketing or some other field? Would I have been successful? I don't know. But I did this because I had opportunities and it was extraordinarily lucky.
Absolutely amazing journey. I'm still amazed by the amount of things you've done. I'm overwhelmed for you. And so we have to finish this Q&A and go to Professor Hugo Thienpont. Thank you so much for your talk. It has been amazing.
Yes.
But,
I'm going to leave you now because I have another meeting I'm supposed to be at.
Sure. Thank you so much for being here and making time for us.
I enjoyed talking with you all. Yeah, bye-bye.
Bye-bye.
How do I get out?
Oh, the end button in the bottom right corner.
I need to stop my share. And there we go. Yeah.
All right. I'm just going to say a few words about Professor Thienpont. His talk is going to be about bringing photonics solutions to industry, all changes, great and small. And I don't think anybody can describe or introduce Professor Thienpont better than John Dudley, who said, for more than 3 decades, Professor Thienpont has been one of the international leaders in his field. He has developed and pioneered world-leading infrastructures and collaborative initiatives. He has supported the creation of new companies and startups, and he has worked in science communication and outreach from grassroots to policy. His all-encompassing commitment has generated a coordinated photonics community within Europe, while his own research has always placed the needs of society at its heart, attested to by the very structure of his research institute at VUB, namely B-PHOT. Again, I cannot cover everything in my introduction, so let's hear from Professor Thienpont. The floor is yours.
Thank you so much. I hope you can all hear me well.
Yes, we do, loud and clear.
And you can see my screen that I shared with you.
Yeah, sure.
Yeah.
So first, before starting my presentation, let me say a few things. Let me first of all say thank you for inviting me. I think we are all busy, but when the SPIE Elsa Student Chapter asks me to give a presentation, I'm more than happy to do so. Secondly, I just wanted to say how thrilled I was to hear Professor Garmire. Let's not forget, these are the people that 50 years ago made the laser what the laser is today. They made it all happen. They turned the laser, which was a solution looking for a problem, okay, they turned it really into a practical thing. And that laser revolutionized our economy and is at this moment absolutely changing the world we live in. It has been the basis for photonics, and photonics is shaping our present day economy and our industry. And I think I'm going to quote Professor Garmire with one of the things he just said. A market economy, an economy of scale is defining the future of photonics. And I couldn't find a better introduction or a better quote to start this presentation, because my presentation is actually all about bringing photonic solutions to industry. And there are a lot of challenges, and I'm not going to name them one by one. I'm going to invite you, while I'm going through my presentation, to discover those challenges. Some of them are smaller, some of them are greater. So that's why I called it All Challenges, Great and Small. Maybe I can say, first of all, that our today's economy and our present day society is really very much driven by knowledge and innovation. And of course, that knowledge and innovation is driven by partially the academic institutions, the research institutions, but to bring those ideas from research institutions into products, you need companies. And I'm going to focus a little bit on Europe, because that's, let's say, where we live. And in Europe, the motor of the innovation economy is driven by SMEs, small, medium-sized enterprises. And maybe that may be different to you or new to you, but there are more than 24 million small or medium-sized enterprises in Europe, and they make up more than 99% of all the businesses. Okay, 2/3 of them account for all the employees that are there, and about 260,000 of those 24 million SMEs are classified by the European Commission as really innovative companies. Now, if you want to innovate, you need new technologies, and the European Commission has identified 8 key technologies that enable the process of discovery and innovation, and what is recently called, with the new buzzword, digitization. You see them all here. I think you heard a lot about them. The one I'm going to talk about tonight is, of course, photonics. Photonics, very simply said, the science and technology that innovates with the unique properties of light. And what I mean by that, by unique properties of light, is light and photonics is not always the best solution. It is only in certain cases that optics and photonics outperforms any other technology. And that's when you have to understand, that's when you have to choose to use photonics. I think Professor Garmire said it's about cost. Well, cost determines, or cost is an important factor if you want to be successful in bringing or turning an idea into a product, and photonics can really help also to bring down that cost. Photonics, a key digital technology. I think you know how it revolutionizes our life. Optical telecommunication, we can't have this conversation over the internet without optical fibers. The photovoltaic cells on your rooftop to create electrical energy. The LED lighting, very durable. Display technology, the lasers in manufacturing are really booming. There's a lot of photonics in the biotechnology, but also in the medical world, there's a lot of optics. There's machine vision. There's so much that's happening with photonics, and Europe takes a very strong position in photonics on the global scale. That means Europe is strong in the market. The total market is about 660 billion euros in 2020. So these are recent numbers from March 2021, brand new. Europe takes a total share of about 16% of that market. And that market is growing with 7% per year. And that is one of the fastest growing fields in the world. There's not many other industry sectors that grow as fast as photonics. And the average growth of industry and industrial production is about 1.5% per year. Photonics grows with 7%. That's 5 times more, okay, 500% faster than any other, than the average production. What is also important to know is that a lot of that industry is injecting 10% of their revenues back into research and to development and into innovation. And I think that's for all of you a really important message, because it means that research is of course done in research institutes and at universities, but there is also a lot of development in the companies because they really invest a lot of money in there. There are more than 5,000 companies in Europe. Most of them are small and medium-sized enterprises working directly in photonics, employing 380,000 people. That means it's a bigger business and a bigger industry sector than the electronics in Europe. And a lot of people find that hard to believe, but it is the case. Here you see a graph where on the x-axis, we see the share in percentage of the market that Europe has for certain industry sectors. And on the y-axis, you see the growth, the percentage in growth. For example, lasers in production, Europe has 50% of the world market, and it grows with 5%. In the case of, for example, medical technology, Europe has about 30% of the market, and it grows with 5%. So Europe is very strong in lighting, medical technology, machine vision, production technology, somewhat in data communication, but we lost, for example, the display market. Now, what you have to know is that besides the 5,000 companies working in photonics, there are 260,000 high potential small and medium-sized enterprises that could benefit from photonics innovation. Okay, we call that the use of photonics as an enabling technology, not photonics for the sake of photonics, but photonics to enhance other products, other industry sectors. So let's just take a look at them. In health, for example, photonics can do a lot. In the digital infrastructure, photonics is really important. The same holds for mobility, energy, safety, security, space, defense. In the agroeconomy or the food industry, photonics plays an important role. And as I said, in the manufacturing, lasers in manufacturing for welding, really important. Just to give you a couple of examples, in the data communication, fiber to the home, and as you will see, there's a couple of names of companies here with whom B-PHOT has been working recently in Flanders. So fiber to the home really becoming important. Here you see Tomra Sorting. It's a company in Belgium where they do laser scanning for food sorting in order to make sure that the defects are taken out of the food stream. The LiDAR, we are currently working with Xenomatics, a Belgian company, to develop LiDAR for self-driving cars. With Barco, we've developed a laser projector of 60,000 lumens for 3D experience in the cinema rooms. Also with Barco, we developed medical displays, really important if you want to look to the high resolution scanning images. ETAP is a lighting company with whom we developed LED LEDs, LED lighting, and with Materialize, one of the very early companies, but a Flemish company in 3D laser-based metal printing. We're currently working on their optical system, just to show you that both there are photonic companies, but also a lot of non-photonics companies that are enabling their products with the special properties that photonics has to offer. Now, so the core message to you is photonics, it has an importance in its own right, but photonics is slowly but steadily also invading a lot of other industry sectors. And that is something that up to 10 years ago, 5 years ago, we could not say. We were all working on photonics components, on lasers, on fibers, but today photonics is supporting a lot of new industry sectors or existing industry sectors. And that is, in my opinion, one of the biggest revolutions and disruptive changes that is currently happening. So optics and photonics is really helping a lot of the companies to go through the digital transformation, to increase their competitiveness. And for all of you, really important to understand, the European Commission is focusing on photonics as a key digital technology and wants us to keep that technology in Europe. It means that we have to all work on making sure that we will stay on top of that technology that photonics is, that great and fantastic technology, and we call it making sure we keep our technological sovereignty. Okay, so we don't depend on China, we don't depend on the US for these important technologies. Finally, Europe is heavily investing in photonics because photonics is a sustainable technology. It is really part of the Green Deal. It's one of the most energy efficient technologies, whether we're talking about data communication or in the manufacturing. And of course, Europe is supporting the Sustainable Development Goals of the United Nations, where a lot of other very, very important topics are coming up where photonics can absolutely make the difference. Now, if you would be a company and you would like to innovate with photonics, then you are facing certain roadblocks. You are facing certain challenges, okay? And what are those challenges? First of all, most of the companies that would like to innovate with photonics do not have photonics expertise in-house. They do not have photonics experts in-house, okay? That's certainly for the non-photonics companies, but there are also a lot of photonics companies that have, of course, photonics experts, but that are lacking a lot of other expertise in photonics that they do not have in-house. So whether you're a photonics company or non-photonics company, in many, many cases, you will be missing expertise, okay? And then there are several ways to get that expertise. You could find that expertise by going to shop to other companies, okay? And we call that multi-stop technology shopping. It means a company that doesn't know about photonics goes to a photonics company for the design, they go to another photonics company for the prototyping, and they go to another photonics company for the mass manufacturing. But of course, the one that has to do the mass manufacturing says that the prototyping is not good or is not okay for mass manufacturing. The person that has to develop the prototype says that the design is not good. So very often, a lot of those multi-stop technology shops or shopping with different companies, the only thing you get back is knowing that the solutions they offer you are very incompatible. So you're back to zero. A lot of the companies think they need to invest in technologies. I don't think it's always a good idea. Investing in photonics is hugely expensive. Paying the expertise is hugely expensive. So I personally think they do not always have to have the top technology in-house. My suggestion would be, why don't we create something where we provide the photonics expertise and we do an open access of the technology platforms that are available in our universities and that are available in the research institutes. This way, we can really help the SMEs and support them along the entire innovation valley of that. Because if you're a company and you have an idea, and we call that the idea technology readiness level 1, you just have the idea, okay? There's no prototype yet. If you have a prototype, you're at technology level 3. If you have many of those prototypes and ready to upscale, you're at technology readiness level 5. And if you're really commercializing, you're at technology level 8 or 9, okay? So if you're a company and you have an idea, the first thing you need to do is make a prototype. If you have a prototype, you have to scale it up for production. And if you have that scaled up version, then you really need mass manufacturing to go to the market. So there are, in that entire valley of that, between idea and product, there are several, what I would call, critical chasms that we need to cross. From idea to prototype, from prototype to upscaling, from upscaling to the mass production. So if you're a company and you'd like to do that with photonics, or you'd like to improve your products with photonics, you need a lot of help. The first thing is orienteering. People that tell you where to find the best experts, where to find the best technologies, and what are the best technologies to support you. Then you have to find that group that will actually help you with innovation support from the TRLs 3 to 8, because you as a company have an idea, but you don't know how to fabricate that. So you have to turn it into a prototype, you have to upscale it, and then do the mass manufacturing. So you need, at those 3 levels, all that innovation support you can get. Very often, and that may surprise you, the companies do not always have a good business plan. The business plan tells you how you have to move forward, also financially, in order to make that idea, turn it to a product, bring it to the market quickly enough, and make sure you make a profit. So you need a good business plan. And a lot of companies do not have good business plans. So companies also need business coaching, especially in a market that they don't know, and that is the photonics market. Finally, if you're a company and you really want to go from A to Z, from TRL1 to TRL8 with a new product, you need a lot of money, and you don't have that money. So you're going to have to look to what we call venture capital. People with a lot of money that believe in your idea and that want to put that money and provide you with that money in order to make your dreams come true. But of course, they will not just give you that venture capital. They ask something in return, a fair share of your profit, of course. So if you as a company want to innovate with photonics, then the best you can do is make sure you are working, you're networking, you're collaborating with the best people, the people that give you the best orienteering, the best innovation support, the best business coaching, and the best investment coaching. And so the idea that the European Commission had is, why don't you put all that support into one big consortium? Why don't you put that into one stop shop, a single stop shop? That means the company knocks on the door of a certain association, and that association can help the company from A to Z. They can help them with deep technology support. They can help them with coaching. They can help them with financial coaching and business plans. And the European Commission has called such a kind of place, such a one-stop shop for innovation support, a digital innovation hub. That's a new buzzword. And we have tried to create such a one-stop shop for photonics innovation in order to support both photonics companies and non-photonics companies with all these different services. Okay, and it's called Photon Hub Europe. Photon Hub Europe started this year, the 1st of January, and we received from the European Commission about 20 million euros in order to make this happen. That's a lot of money, but that, of course, is something that we need to do in order to deserve that funding, and that is to support companies. Now, we don't do that alone in Brussels. We have 54 European partners. 36 of those partners are partners that will, together with us, do the technology support. That means we have a lot of equipment, we have a lot of technology platforms. I'm going to introduce them to you rather quickly. And we are going to team up together. We're going to select teams from all of those different groups and make sure we help the companies. How we do that, I'm going to explain that to you immediately. We also have a couple of special partners that will do the business coaching. But of course, we did not get that project from the European Commission just like that. In fact, we have been working for 15 years on different ideas. We have refined those ideas to see how we can best work with companies. Working with companies is, as a university, is not simple. So the first thing we've done in 2004, that's almost 20 years ago, is we created networks of excellence. These are networks of research partners in Europe that will compare their technologies and that agree to select the best technologies available and to make those technologies available to companies. So it took us 5 years to structure Europe, make sure that we knew who had the best technologies for this photonics technology, who had the best technologies and the best technology platforms for example, for fiber optics, for freeform optics. We identified them, and then we created new projects that allowed us to test those infrastructure, to test those technology platforms with small and medium-sized enterprises. And we learned a lot from that. And then, of course, came the big jump. We were very successful with our first trials. The European Commission said, this is the way to work with industry. So please now move forward. We're going to scale up the funding you get from 1.5 million to 6 million to 10 million euros. And finally, of course, at that stage, we were working with the companies with prototypes. We needed new groups that also could do the upscaling, that had pilot lines, as we call them, where you go from prototype to hundreds or even thousands of components. And here you see the European pilot lines. We then brought together our prototyping facilities with the pilot lines, and we created Photon Hub Europe. So it took us 15 to about 20 years before we fully understood how to work with companies, who are the best experts in Europe, and what are the best technology platforms. The first thing you also have to understand is that in the beginning, we made a lot of mistakes when working with industry. As the title of the presentation says, bringing photonic solutions to industry is in fact a little bit a misleading title, because it thinks, or you could think, that we bring and we push our technologies to the companies. That is the wrong way. That's not the way to do it. The way to do it is to go to the companies, listen to their challenges. Companies never have problems. Companies only have challenges. So don't go to the company and say, what's your problem? Maybe I can help you. No, no. Of course, a company will not tell you that they have problems. But you could say, do you have any technological challenges at this moment? Because we're photonic specialists, maybe we could help you. Or you could also say, do you know what photonics is? Do you know what photonics can do? Maybe you can improve your products with photonics. So it is really going to the companies and listen to their challenges. So that is what we call the market pull. It is us going to the companies, not to sell our research, not to tell them how good our technology is, but just to listen to them and ask them, what's your challenge? Can we help you? And so that means that reaching out to companies is crucial. How do we know where the companies are located that could need our help? So that is one of the biggest challenges you will ever encounter if you would like, from your research group, from your photonics research group, if you would like to work with industry, whether that industry is nearby in the region, whether it's in Europe, whether it's in Japan, in Asia, or in the US. How do you find your customers? How do you find those companies with whom you're going to work together? Okay. And whether that's photonics or whether it's electronics or nanotechnology or biotechnology, it's always the same. You have to show that you are interested in, and you have to show your interest to companies and try to convince them to listen maybe to your story. But in the first place, you should listen to their challenge and see whether you can help. And please don't tell them, yes, we can help you if you can't, because that is the worst start. That is the beginning of a disaster, okay? Never do that. So only say yes when you're perfectly sure you are one of the best people or best groups placed to do that. And once those customers, once those people are interested, you can set up a project. You can make sure that either they pay for the project or you use the European Commission's funding, like we do, for example, in Photon Hub, and make sure that you're collaborating with those companies. Later on, you will see if you do a very good job that they will come back to you. If you did a fantastic job, sooner or later, they will come back to you. So you have to find a good customer basis, start from there. And we are using a pipeline architecture to follow that process. And I'll explain that later on again. What is also important is if you have helped that company, try to measure the impact. What have you changed? How good were you? Have they been satisfied? Did they create new jobs because of what you have been helping them with, etc., etc. So the innovation support pipeline is really important. And I'd like to give you some numbers here from a previous project. It's called Act Fast, something similar like Photon Hub. The first thing that we've done is we've set up press campaigns, outreach campaigns. So we went to exhibits, we went to brokerage events where we talked to companies, we sent out press releases about who we were and what we could do for them. And so we reached about 37,000 companies by doing that. So that's a lot, okay? So the numbers here are really important because we reached out to 37,000 companies, and from those 37,000 companies, of course, that is creating awareness, telling them who we are with video, movies, websites. 400 of the companies came to us. And those 400 companies, they really shared with us their challenges. And of those 400 companies, 180 companies we could really help. Some others we had to tell, look, electronics is a better solution. Please don't use lasers for this. It's not good. Photonics is not the solution. In other cases, they asked us things that photonics could not do. So don't promise what you can't do. And so overall, 180 companies really started to work with us on projects. And finally, about 100 projects came out. So keep those numbers in mind, 40,000, 400, 200, 100. That's more or less, here you see the percentages, and that's the pipeline, okay? That pipeline is important. It's like recruiting students for your SPIE OSA chapter. You have to make a lot of noise to a lot of students if you want to see whether some people are interested, and out of those students, there may be finally a few that register, and some that will really show up at your activities. That's a pipeline, not more, not less. The same holds with industry, with money, with contracts, with research projects, and even with research ideas. You have a lot of great ideas. Some of those ideas you really need to check. Some of them are really worthwhile, and finally, a few of them end up in publication. It's always the pipeline going from large to small numbers. So outreach is important. Marketing, communication, tell the people who you are and what you're doing. And one of the most successful, and I'm sharing that with you with great pleasure, one of the most successful ways to reach out to companies is brokerage events. It's very simple. You have a lot of tables and you have a software, and you check the companies that are available, and you tell them that you'd like to meet with them. And if they accept your invitation, you have 15 minutes to talk to them. You have not more, 15 minutes to tell them who you are, to understand what they do. You have to do, of course, their homework, your own homework. You have to already know what the company does. For example, it's a biotechnological company, and you think that they're working on lab on chip, and you would like to know whether they have already worked with photonics. They don't know about photonics. You tell them what photonics can do. You tell them how important photonics is for lab on chip. And maybe you can start working with them on spectroscopy, on Raman scattering, whatever. And in 15 minutes, you catch their attention. And it's an all or nothing, okay? Because you ask them to contact you the next day. If they don't do it, you lose that company. You lose what we call the lead. But if on one day you meet with 20 companies, and the next day 2 of them come back to you, you've done a great job, okay? So it's tough. So you need business developers who will go and spread the news, who can talk about technology with those companies, and who understand from the point of view of the company. You don't have to sell your technology. You have to listen to the company and say, what are you doing? Have you thought about this? And how can we with photonics help you? Okay. If they don't know about photonics, you tell them about photonics. And 50% chance that they're very interested. Okay. So this is the way to do it. It's very exhaustive. I mean, when I go with my colleagues to these brokerage events, in the evening, I'm almost dead because it takes so much energy. But if the next few days you get leads from industry, then you're really happy, okay? And you know why you spend so much time. There are other ways, I'm not going to talk about them, but you can go to exhibits, have a booth, talk to the people there. It's not so simple, okay, to attract people. So that's really important. Or that is how to create your customers, your leads. Once you get them interested, you can see how you're going to help them, okay? Some of them will need training, you could train them. Some of them are needing business and financial coaching, you can do that as well. but we're going to mainly talk about how we can help them with our technology support. And as I said, when the companies come in, we can help them at 3 different levels. We can help them with creating a new prototype, TRLs 3 to 4. We can help them with upscaling, which is already something very different because you need a pilot line, you need really large-scale facilities where you can go from 1 component to 1,000 components. And we can also help them with accelerating the manufacturing. We're going to do that, of course, in Europe. We're going to advise them where they can find companies that can fabricate the components that we replicated for them in 1,000 or 10,000 components, how they can make millions of them, because that is not what a university should do. A university should not be a company that is fabricating millions and millions of components. We go typically to the TRLs 5 and 6 and not much beyond that. So in Photon Hub, we are offering 8 technology platforms and the combination, of course, of those technology platforms for companies. We have a platform for optics, free space optics, one for polymer optics and flexible optics, one for specialty fibers, one for MOEMs. Like Professor Garmire said, the photonic integrated circuits are picking up interest, silicon photonics, silicon nitride, indium phosphide, and we have a new technology platform on laser-based manufacturing. So we can combine them. We can really combine them, and that is fantastic. And each of these technology platforms goes from design to prototyping to almost mass production and packaging. So that is something we can really offer, as we can also offer, besides the technology platforms for prototyping, the pilot lines for the, let's say, upscaling up to mass manufacturing. What you really have to know if you want to bring solutions to companies is you do not only need a photonics expert. You need people that can lead projects. So you need project leaders. You also need people that can go to the companies and discuss about their needs and their technologies. We call them technology scouts. And you also need people that can help you with setting up your finances, but also that can talk to the company about setting up the project, but also defining the cost of the project, and that can discuss the business plan of the company. And we call those business coaches. So again, if you'd like to work with companies, it's not just good enough to be a good researcher. You need project leading skills, or leave that to some of your colleagues. You need technology scouts, people that can understand and talk to industry, and people that know about the business. And talking about helping companies with technology support, that is really important. But suppose you're doing a good job in that. Suppose Photon Hub is really helping the companies with excellent research and innovation teams and fantastic technology platforms. And suppose that we create prototypes, or we even upscale their devices. At a certain moment, they need to take everything into production. And then they need money, a lot of money. That money they get, as I said, from venture capitalists. Venture capitalists are people that we bring together, people with a lot of money that will listen to the spin-off company or to the young entrepreneur who would like to make a new product. And if they are interested, and if they believe in that new product, they will put their money in that business. Therefore, you have to convince those people that have a lot of money. You have to convince the venture capitalists. You can't just do that by drinking a coffee with them and say how good you are. No, there are strategies, there are ways to really talk to them. And one of the things we do is we are training those young people, and we prepare them to be investment ready. That means we're going to help them, or we're going to coach them on how to pitch, how to talk to those investors. We call it intensive investor pitching coaching. And that is, I think, really important, because you only have one chance. If you screw up, you can forget it. So you may have the best prototype. If you can't sell your case, if you can't answer their questions, if you can't present an excellent team to start up your business, then they will say, it was nice talking to you, good luck. And that's it, okay? So you get one chance, and that means we shouldn't screw up, and we have to prepare those people to make sure they make the best of their pitch, okay? And then, of course, after training, we bring them together to, for example, a forum, a kind of workshop or a conference where they have the opportunity to talk briefly, to pitch briefly to those investors. And in 50% of the cases, they are very successful, and they raise a lot of money so that they can start up their new business, or the existing companies get a lot of new money to scale up their business, okay? So what is important, as I said, is first finding the companies, then working with the companies, making sure that the companies also get the support in finding new investment, and then, of course, also see whether you have made an impact, whether you have changed something, okay? And the answer is, let's first of all look to the new products that came out of those collaborations. And here you see a couple of examples of projects that we have been managing from ActFast and soon from Photon Hub. A couple of examples from Photonics companies. Photonics companies, small, medium-sized enterprises like the German company Phibotech, with whom we have been fabricating new or designing and prototyping new specialty fibers for optical amplifiers. We have been working with indium phosphide frequency comb chips in order to do terahertz generation for the Spanish company Luz Wave Labs. With a Belgian company Lambda X, we've developed freeform optics for head-up displays, and so on and so forth. So these are just a couple of examples of a variety of photonics companies that needed photonics support, okay? There are many others, but I'd rather focus a little bit on the non-photonics companies that received support, so you have an idea of the large variety of topics we have been working on. With an Irish company, they have an affiliation in Belgium, Tomra Sorting, but in this case, Irish company, we fabricated food sorters, but based on LED-based sorting, not on lasers, but on LEDs, because they're lower cost, okay? With a Belgian company called Laser, strangely enough, but they're fabricating cycling helmets, we have been making visor-mounted displays so that the cyclist sees his or her heartbeat projected in that cycling helmet. The Greek company Prime Laser Tech, there we made temperature and pressure sensors, optical pressure sensors, to measure temperature and pressure in solar thermal systems. And with the Italian company Gamma Impianti, strangely enough, we developed UV illumination for bacteria, for eliminating bacteria in the toilets of the trains, okay? So a lot of strange applications. We worked on medical foot scanners with optics. We worked on cardiovascular monitoring of patients that were suffering from heart failure. We created special chips for augmented reality, and so on and so forth. So let me briefly tell you what those companies have done after we helped them with our prototypes. For example, in this case, the company Laser Sport that fabricated the cycling helmets, they came really into the visor, they came into the spotlights because of this dramatically novel product, and they were acquired by Shimano. Shimano, a very large company that is, of course, fabricating bikes, but also all kinds of accessories that cyclists use, like this cycling helmet. So these guys all of a sudden saw their startup being taken over, and they received a lot of money for that. A very strange other type of demonstrator comes from ABC Harden, who are making fireplaces, typically fireplaces with wood or fireplaces with gas. But as you know, they are quite polluting. And so there are new EU regulations. And so these people came to us and said, can't you help us? We heard about holographic fireplaces. So we created with them a kind of really fantastic 3D, you should see it, it's amazing, fireplace that is based on liquid crystal displays and optical coatings and etc. etc. And so what they did is they fired all their mechanical people and they hired photonics people in order to create this. And that is just that made them survive. Otherwise, they would have gone bankrupt. They would have stopped their business. Now they are at a lot of exhibits with their holographic fireplaces. Just a great story. Lambda X, I explained you, had up displays for avionics and car. They immediately were able to hire a lot of new people and increase their revenues. The same with Skylane Optics, who made optical transceivers, and we helped them with making these optical transceivers for plastic optical fiber. They immediately hired a lot of new engineers, photonic material engineers, photonic engineers, and then they went to the European Commission for getting new funding, and they raised 1.5 million euros, and they were able to continue working with us on this new product. Other companies like Technobis, with whom we made optical sensors for the avionics, they grew so fast after their first prototypes and the successes they had with that they had to go to a new building. Okay, an Irish company, Pilot Photonics, with them we developed optical frequency source comb sources. Though with their prototype, they went to the European Photonics Venture Forum, came out as a winner, and I think the last couple of years they raised 3 to 5 million euros, and now they're booming. They're hiring a lot of people. They're just a fantastic top-level, fast-growing company in Ireland, and so on and so forth. I could go on, like in this case, Holoxica, making holographic medical displays. We made high-quality diffractive optics with them. Again, they went to the market to find the new funding, and their business is booming. All of this because we, at the academics institutes and at research institutes in Europe, we teamed up, we worked with them, and we created new prototypes, and that is really the impact. It's not only the new products, but let's look to the quantitative impact that we created with ActFast. Overall, more than 60,000 European companies received some news from us on how important photonics was. And as I said, we have a pipeline. We were not able to help all of them. Eventually, we helped 120 of those companies with deep innovation projects. Those companies came from 25 member states in Europe. That means from all of the member states, we had companies. So they really came from Greece, from Denmark, from Sweden, from Ireland, from Spain, from Portugal. We served companies from all over Europe. 90% of the companies were SMEs. 65% of all the companies that we worked with were non-photonics companies. So the biggest business will not be photonics companies, but the biggest business for the future will be non-photonics companies. And that is all the more true if you know that 35% of the companies we worked with never heard of photonics before. So companies that didn't know what photonics were or was, we worked with about 40 of those companies to create new products. I think we got a score of very good with almost all of the companies we have been working with, so they were really, really happy. The total of new venture capital that was created is about 75 million euros. That's a lot of money for 10 companies. 700 million euros new company revenues and more than 750 new jobs. That's what we've done in 4 years' time. So I think it's really important to see that universities, if they team up, if they select the best experts if they select the best technology platforms, and if they listen to the company's challenges, and they can work with those companies by selecting the best experts and the best technology platforms, they can really make a difference. Yes, we can bring photonic solutions to industry. There are a lot of challenges. Some of them are small, some of them are great. But in any case, the first thing you have to remember is you can support companies with photonics innovation, but only when you listen to their needs, okay? That is really important. You have to listen to what the companies, what their challenges are. Secondly, you need a huge amount of experts and cutting-edge technology platforms that almost cover everything you should have in-house to help whatever a company needs. So you need a lot of experts. With Photon Hub, we have that, 500 experts. You need a lot of cutting-edge technology platforms, and you have to make sure that those technology platforms that you can offer are comprehensive. That means that you can solve almost all of the problems that a company can have in photonics. What's really the biggest challenge is create visibility. Make sure that the companies know you are there, that they can rely on you, and you have to reach out always to those companies, because otherwise you will never get a customer. That is something you have to do on a daily basis. Not once, not twice, not every month, but every day. It's also important to understand that if you want to really help companies, you have to help them, give them a helping hand while crossing the full innovation valley of depth, from TRLs 3 and 4 to 5 and 6 to 7 and 8. That doesn't mean that we at universities have to do everything ourselves. We can cope with the TRL levels 3 and 4. Some of us can cope with TRLs 5 and 6, and the production will leave that up to the companies. Okay. It's also really important not only to provide technology support, but also business support and financial coaching, and in some cases, training. Some companies will come to us for training, and then you have to make sure you listen to them, and you will train their people, and you will learn a lot by working with those people from industry. Because if you help them, and if you can show them what your knowledge and your skills are, they will come back to you sooner or later, okay? Because they know what you can do. So training people is one way to generate new customers, to get in touch with companies. And finally, measure your impact. See what you have been changing, how you have been changing the world, how you have been creating together with companies new products. Tell that to the world. Make sure that the companies are grateful to you and that they will be your word of mouth advertisement. The best advertisement is a company that tells another company, go to Photon Hub or go to Brussels Photonics or go to any other partner because they really live up to your expectations. That is 50% of our customers. 50% of our customers is because other companies have said to those companies, please go there. We were happy, you should be happy as well. So we can make as much advertisement as possible. That only gives us 50% of the customers. The other 50% is by word of mouth, okay? And that is because a lot of the companies are really happy with our support. We call them our star performers, and they will do eventually the outreach for us. So that is, I think, the way to make sure that we can bring photonic solutions to companies. When you can tackle those challenges, I think we will be able to win Europe's future and make sure photonics can thrive and make sure that Europe lives really well in the age of light. Thank you so much.
Thank you so much for your talk. I can say I'm very, very much awed and inspired by everything you said. I learned a lot. And Well, I'm going to ask the first question, and it's a really important one for us in the chapter. We can see that you have contributed a lot to society, to the field, and I guess that's why you've won the SPIE's gold medal. I would appreciate any comment you have on that.
Well, let me first of all, well, one thing I really want to tell all of you is that it came to me as, and most probably you have read that in the news items, but the SPIE gold medal came to me as a true surprise. Okay, I won a lot of awards. I had the ICO award, I had the SPIE President's Award. I mean, there's many awards. An award from Japanese colleagues for micro optics. Many awards, and all of my awards, they came unexpectedly. I never applied for an award. I know a lot of colleagues, and they have the right to do so, that are chasing awards. I'm not chasing awards. Okay, I don't really, I mean, it's nice to have an award, but only when it's unexpected. Okay, it's really true. I mean, suppose you are submitting to so many, you're submitting your candidacy for so many different awards, and then finally you get one of those awards. I mean, what have you done? You have really chased awards, and then you have one. I mean, how can you be proud of that? I think what I really like about these awards is they came spontaneously. My colleagues, both national and international, one way or another, teamed up. They proposed that I should get the award, and then an external commission is looking at this, and then they decide, yes, he deserves this. And then all of a sudden, in the evening, while I'm having a glass of red wine, I'm looking to my mail. All of a sudden, I get this message for SPIE gold medal. And I sit to Natalie, next to Natalie. You know, Natalie Vermeulen is my wife. I'm sitting next to her. I said, "Do you know what? Do you know what? Look, what is this here?" I said, "I have the SPIE gold medal." I said, "Can't believe this." So I read it, and it seems to be true. So I think this is it's really nice. And I think I received it not because of an invention or not because of important papers. I think it's just a kind of lifetime achievement. But that means that I'm getting old. Okay, it means I'm closing in on retirement, which is a little scary. Okay, but if I see how Professor Garmire is still on top of the technology, it gives me good hope.
That's great. We're very happy about this achievement, and on behalf of the B-PHOT Student Chapter, we congratulate you. And with that, I'm going to go to the audience questions. So firstly, Yusuf Purwais is asking, how can a recent PhD graduate of photonics with an idea start their way towards SME?
Sorry, can you repeat that? Because
yeah. So how can a recent PhD graduate of photonics with an idea start their way towards SME?
Okay. So how can a PhD student or somebody who recently got a PhD, how can they actually start their SME, or how can they work towards an SME? Well, the first thing I think you have to do is you have to understand what a company is. And that doesn't necessarily mean you have to work in a company, but you could work with companies. So, you know, at B-PHOT, there are a lot of postdocs that we have that really like working with companies, but they don't necessarily are hired by a company. They stay at B-PHOT and work with us with companies, okay? That is the first step. You have to try to understand their language. If you don't do that, you will never be able to really set up a good or your own company, your own business, okay? So learn the language of the company. You can do that, of course, by going for or by following entrepreneurship courses. I can recommend that to everybody. VUB has very good entrepreneurship courses. Very soon, also digital courses, MOOCs that you could follow whenever you want. That is something you certainly should do. But the practical experience is just is invaluable. Okay, and that practical experience you get by working on small projects, for example, Act Fast projects or Photon Hub projects. So if there are PhDs or postdocs that would like to stay with us, with B-PHOT, working on those projects to learn, that is just fantastic. We give them all that type of opportunity. Even we give certain PhD students the opportunity to work on those industry projects, short projects. Why? Well, only of course when that has to do with their PhD topic, but as such, they do both the scientific aspects, or they follow the scientific aspect, but also the industrial aspect. And it gives them a flavor of what industry does, what the applications are, what a business plan is, how to set up a project, how to write a project, how to estimate the costs of a project, and then to do the real interaction with the companies. And again, I can't say it enough, it is invaluable to do those type of projects. Even if you would leave B-PHOT after 3 or 4 years, if you would tell us, I'm here to do some experience, to gain experience in working with companies for the first 3 or 4 years, and then I may start up my own company, or I would go to other companies, that's fine, okay, we know, okay, and then you work with us on those projects. It's never one project, it's 2, 3 projects at the same time with different topics, and that makes it so fascinating. That's why a lot of the postdocs stay with us and work with us, because working in one company on one topic is maybe not as enthralling as working on 2, 3 topics at the same time. Okay, so that is already two things. But of course, if you want to start up your own company, you need a great idea. You need an idea is not good enough. You have to make a proof of concept demonstrator, but there is plenty of funding for that also at VUB. And then there are several fellowships you can have in order to bring your proof of concept and turn that into a startup. And at that moment, our tech transfer office comes into play, and they will really guide you and help you with your business plans and creating your team and making sure you protect your intellectual property, your new ideas in the form of patents or ID depots, etc., etc. So it's a very long story, but it's a very fascinating and interesting story. And some of us have done that. So we created startups. We're actually again having several ideas to create startups. But one of the things I'd just like to share with you is whenever you start up a company, what you typically do is you take with you several colleagues that you know and with whom you like to work. Okay, you need their skills, you need their expertise. Setting up the company on your own with you as the only employee, that is almost not done. Okay, you need a team of people, which means that if you would leave B-PHOT with your idea, B-PHOT of course will help you setting up that startup, but it means that most probably you are going to take also colleagues with you, and that all of a sudden we will lack a lot of expertise. Okay, because you go your way and several people will leave us, and that is always difficult, is finding the right balance between spinning off a lot of companies and still not losing your expertise. Okay, if I would have set up companies every time we had good ideas, there would be nothing left of B-PHOT. So you have to find the right balance. Okay, that's my final advice there. But I'm much in favor of spin-offs on condition that it's not a wild adventure. Okay.
A very wholesome answer indeed. So the next question is from Olga. Do you foresee any changes on the growth of the photonics field due to COVID?
Okay, it's a very good question. It's a difficult one to answer, but the good news is that, of course, we are in touch with a lot of small and medium-sized enterprises and industry. And at the same time, I'm Vice Rector for Innovation and Valorization, which means that we have a good idea of what's happening in photonics at this stage. And we have launched a survey recently to the companies, especially to companies we have been working with ActFast and with Photon Hub. And the answer is that most of the companies are doing a better business during COVID, and that's the good news. Okay, and strangely enough, I couldn't believe my eyes when I saw the outcome of that survey, but most of the companies said we don't have a negative impact of COVID. We are not inhibited, we are not slowed down by COVID in our innovation activities. And I can also tell you that at university, for the time being, we don't see any impact in the number of collaborations between university research groups and high-tech companies because of COVID. On the contrary, what we do see is that the access to the labs is not so simple, but okay, that is something we need to cope with, and hopefully in this and half a year that is over. But a real negative impact in the photonics industry due to COVID, no, I would say on the contrary.
So the next question is about the international people that actually come to Europe or come to B-PHOT. So they don't have a permanent residency here. Would they be limited by EU rules? Maybe it's a bit technical, but would they be limited by EU rules if they want to start their company or run a company?
No, I don't think so. I think what they can, I mean, first of all, being permanent in the European Union, I think like in the States, etc., it takes time, okay? But as soon as you have a job and you can be self-sustainable financially, you can be sure that the chances are high you can just stay in the European Commission. You have the opportunity that actually you can go everywhere in whatever country of the European Commission. You can settle down, start your company, and we don't really care where you come from. I think what is really important is that you try to support society to the best of your abilities, and like everybody else, you pay your taxes, you stick to the rules, and you work hard. Okay, I think there are a lot of signs that we are just attracting a lot of people from internationally. That means from India, from China, from the US, from South Africa, from Africa, where we don't care where the people come from. But look to B-PHOT, 17 nationalities, okay? And if you look to the postdocs, there are a lot of nationalities there. And now, very soon, I mean, you see that more and more professors. I mean, Fabian Dürr comes from Germany. Martin Wirth comes from France. There are a lot of people that are becoming professors that have different nationalities, and I'm pretty sure that some of the postdocs of B-PHOT at this stage come from outside Europe. And in this and several years' time, I'm pretty sure if we can continue to grow and thrive, they will be professor at the university. And some others will start their own company. And some others will go and work in the photonics and non-photonics companies. So I think there is place in Europe for everybody who plays by the rules.
Yeah. So the next question is from Carlos Diaz. He says, because of the roles that you mentioned in the process of starting an innovation project, what could be the ideal number of people who are going to start these projects?
Okay. Yeah, I just wanted to go back to the slide, but so first of all, you need one project leader for 3 or 4 people. Okay, one project leader for every 3 or 4 people that do the work. That doesn't mean that the project leader should not work. The project leader can also be part of the work. Okay, but one project leader for 3 or 4 people per project. I think for 4 or 5 projects, or maybe 10 projects, you need a good business developer. So at B-PHOT, we have 2 or 3 business developers already. Okay, and the scouts, they can be experts. So if you look to B-PHOT, we have about 3 business developers. We have maybe 20 experts that work with industry. And we have about 7 or 8 people that are managing the projects. What I want to say is that what you should do is the things you're interested in and you feel good at. Okay, if you like, I mean, there are a lot of even postdocs that I know that really like the work of an expert, but that don't like to be the project leader, that don't like to write the projects. But there are other people that say, I really like writing the projects and coaching and doing the project leadership, while of course still also doing some technical work. And then you have business developers. Business developers, that is a very special type of people, okay? They have to know a little bit of everything. But especially they have to know how to talk and how to listen to industry. And in our case, we have 2 or 3 business developers, and most of them are familiar with photonics, but most of them did not have a training in photonics. Okay, that doesn't mean that you can't be a business developer if you have a photonics engineering degree. On the contrary, you could develop yourself and turn into a business developer, and then you would be just a fantastic photonics business developer because you know everything about the technology, and you also know a lot about how to develop that business. Okay, but so far we didn't find so many people who are doing that. So that's a niche. So I think B-PHOT has a very nice size, a critical mass. So we have 80 people, about 45 people are technology, are photonics experts, and about 20 of those are really working with industry, mainly postdocs, and about 5 or between 5 and 8 are project leader, and 3 business developers. That's a little bit the ratio you have to keep in mind, because that works well. That really works well.
All right, the next question is from Irina. So how can an early stage researcher work his or her way up and be a part of the Photonics Hub? I think that's a question that a lot of people have right now. Okay,
I think we are open. We at Photon Hub are open to everybody. Of course, if you're okay, let me say it differently. If you're a PhD student, you should first of all focus on your PhD and get your PhD. However, if you are interested in industry projects, you just let us know. And the typical way we work is we give you the opportunity, if there's a project that you can really handle, because let's not forget, you should have certain expertise, but if that expertise is what you have, and you'd like to take up that industry project for 4 or 5 or 6 months, we allow you to do so. and we take that into account, and we give you that additional time for your, or if, for example, suppose you have been working on the project for 3 months, then we give you 3 additional months for your PhD, to finish your PhD, okay? So that's our way to say, it's great, you still get your 4 years for your PhD, but if you're interested in industry projects, we give you that opportunity and you don't have to pay a price for that, okay? So I think that is very, on the one hand, very generous from us, but it's also a way to make sure you're not purely the academic engineer or photonics engineer, you're also, you have also some acquaintance with working with industry. And of course, we're going to coach you. And if then you're further interested and you have your PhD and you'd like to work with us and we think you're the perfect person, then you can continue working with us. There are even masters in photonics that said, I'm not interested in a PhD. I'd really like to immediately work with industry, but I will stay in B-PHOT. I would really like to stay in B-PHOT because that gives me the opportunity to work with a lot of different companies rather than choosing one company. Okay, my daily work is very is multifarious. I can do a lot of different things with a lot of different companies, and that is what really excites me. And that's why I would like to stay at B-PHOT. That's perfectly possible as well. There are a couple of people, and we get more and more people asking us this. Okay, and I think that's really good. Because in some cases, I mean, there's a difference between working towards a PhD, where you really want to deepen yourself in a certain topic and become an expert in that topic and learn how research is being done, how fundamental research is being done. In the other case, it's more engineering tasks that you take up, but there you learn what industry needs and how to work with industry. Okay, you can do both, of course, as well. Huh? Get first your PhD and then do the rest. Or what also you can do is you can choose a topic for your PhD that is an industry related topic, and also that is perfectly possible. Today we even have people that do a PhD while they are in a company working with us. So there's a lot of things that are possible. We just like to discuss these things with you, take the time to discuss that with you, making sure we coach you to the best of our abilities, and making sure you don't make mistakes in choosing things. I mean, you can make mistakes, but we try to give you as much information so that you can make the best choice.
Brilliant. You're running late, so we have 2 questions I see. Let's go over them quickly. How do you think projects like Photon Hub may impact how science in photonics is done?
Okay, that's a tricky one. Science is science, and Photon Hub is industry support. But what we learn, for example, I will give you one example. I think a really important one. In my career, together with my colleagues at B-PHOT, there was a time when we were developing our own technology. That was part of our research. We were working with what I call deep proton lithography. We created a new way to make micro optics, okay? And that was with ion beams and a cyclotron. And we created our own diffractive and refractive components and fiber couplers with that new technology. So we spend a lot of time on developing that technology. And we tried to work with that technology with industry. And industry was interested, but as soon as they had our prototypes, they said, oh, they are fantastic prototypes. Now the question is, how can we scale up those prototypes? And then we saw that our technology was absolutely immature for the manufacturing. And so one of the things we learned by working together with industry is that if you really want to make a dramatic change, if you really want to bring your ideas and your research to the market, okay, and not just publish and publish and publish and do nothing beyond that. If you really want to bring your ideas to the market, then you have to do your research with equipment that allows mass manufacturing. And deep proton lithography was not one of those. So we stopped it. And there was a hard and a tough decision. And then we bought new equipment, injection molders, diamond toolers, etc., with which we could do the mass manufacturing. And at that moment, the amount of components, the amount of projects we had was booming. So we learned this from projects with industry. And I think a lot of research groups that are now partnered in ActFast and in Photon Hub are going through that motion, are understanding that if they want to help companies, they also need to adapt their equipment. And once you have understood that, then collaboration with industry and transferring photonic solutions to industry is much simpler, is much more straightforward, okay? And that is something that we learned from projects like the ones we had in ActFast and in Photon Hub. And so that is profoundly changing the way we do our research now. You will never see me developing an in-house technology. You will see me working with the cutting-edge, commercially available technology to come up with new things. For example, the nanoscribe is cutting-edge technology to photon polymerization, cutting-edge technology. We buy it rather than developing it ourselves. And then we focus on new devices. That is, I think, something that profoundly changed the way we do scientific research, thanks to what we learned from industrial projects.
Amazing. Last question, David. It's going to be really quick.
Yeah, maybe then in a few words, or like maybe the last 3 words. How do you predict the future? What are your 3 words you would say? What are the 3 things you need to do that?
Well, predicting is very difficult, especially when it's about the future. I think Enrico Fermi said that, okay? In 3 words, I can't do it, but what I can tell you is I'm not living in this world today. I mean, the reason why I'm director of research of B-PHOT is because I'm living 5 years in the future. When I just submitted my project for 5 million euros, when I just wrote my project for 5 million euros of new technology, high-tech equipment, and when I submitted it, I was already thinking about the next 5 years. And I was considering my project proposal already to be granted. And when that equipment will be bought, then my researchers will start working with it, but I'm living 5 years ahead. And I think that is something that is the most difficult to do. That is, what is your roadmap? Where would you like to go with the group? And therefore, we have very often brainstorms with the group of people we work with. We ask, where would you like to go? Where would you like to go? And listening to all of that, you have to analyze it and extract and make sure there is one common vision where everybody sees I'm part of that vision, and the top of the group is thinking about me, and I can do my thing that I really want to do. So you need 1 or 2 or 3 people, or maybe 5 or 10 people that together decide about the future and that take the risks. And every year you have to look to that roadmap and update the roadmap. Okay, it's not like now we're going to see what we're going to do in 5 years' time, and we start and we never question ourselves along the road. That's not the way. Okay, but you have to think in 5 years from now. I wrote just 2 big projects, and all of them are asking me to create a plan for the next 5 years and the next 7 years. That is not easy, okay? So you can be very clear for the first 1 or 2 years, And then all the rest is a little bit more fuzzy, but still you have to know what the great lines are, in what direction you're going to move forward. And you have to adapt that vision. But I can tell you that predicting the future for us has not been too difficult, because when I look back to the last 20 years, we are now where I really wanted to be 20 years ago, okay? And still, when I look to who we are today, I'm amazed that we made it. So it's something strange, okay? But the future is something you have to work on a daily basis and update it on a daily basis. And make sure that in some cases you have to dare to take different decisions and say, I was wrong. And in some cases you have to persist and say, I'm not there yet, but I'm going to give it everything I have to make it happen. Yeah, it's a lot of contemplation and thinking and checking. How do I progress, and am I really going in that direction? That is a little bit predicting the future.
Amazing answer. Amazing answer. Thank you so much for your time. We all know that your schedule is really busy. Thank you so much for setting aside this amount of time for us. We have to close the Q&A session now, and I think close the whole session. But before that, I would like to ask you to stop sharing so that Martin can actually present the winner of our photo contest. Martin?
Right, yep. I'll just share my screen. I hope you can all see it.
Yeah.
Yeah, first I really have to say that we had many submissions, and it was very difficult for the jury to pick just 3 of the pictures. We had several criteria, but now we have the 3 winners, and we'll start by the 3rd prize, which is a glance through refraction of Olga Rusiakina. Applause for Olga. The photo shows a well-known symbol of Belgium. That's a description that Olga wrote from a perspective of refraction. The image of atomium and its surrounding appears inverted when looked through a glass vase filled with water. This happens when the object is positioned far away from the refracting medium and an observer. The real image could be obtained when the vase and the objects are of similar size and are brought closer to each other, which in case of atomium would require 100 meter square vase. And atomium height is 102 meter, and the giant as a photographer. The angle and the distance of the camera are chosen to place the image of atomium into focus. So congratulations to Olga, and thank you for submitting. And now we go to the 2nd place, and we have Smiling Sky by Metat Lotfi Chobare. This has a rather simple description. It's a beautiful rainbow formed by small droplets of water in the sky, and we particularly like this photo because it illustrates a very well-known phenomenon of scattering. And then we go to the 1st prize, which is Lithomium painting of Mathilde Patin. Congratulations to Mathilde again, and I'll read the description very quick. Every evening from dawn, the atomium lights turn on. Just placed under the structure at night, I use the lights from the atomium to create an abstract street art painting. Usually art paintings are created by handling a light to create shapes. Here I use the street light to form circular patterns. Looking carefully, you can recognize the spheres of atomium. So congratulations to all winners again, and we very soon will send by post your well-deserved prizes. Just before ending, I'd like to remind you of an upcoming event. the Nanofabrication Photonics online meetup, which is organized by B-PHOT in the context of International Day of Light by Professor Natalie Vermeulen and Dr. Tadevik Jailan. We'll have 2 speakers from our department, our director, Professor Hugo Thienpont, and Professor Jürgen van Erp. So please stay tuned and join in the event. Thank you, and congratulations again.
You are muted.
I think Arash is still on mute, so.
Oh, no. All right. Thank you so much, Martin. So Astrid, will you please take the picture, to take the group picture? Can everybody please turn on your cameras so we can have it?
Yes, and thank you very much, Josh. And if you want, you can use this picture as a background. What just now I sent, like the light night. And please smile.
Look at Chin's baby.
Oh.
Please smile and wait just because I need to take a few pictures. And we are second page. Smile. More people are coming. Nice. Nice, nice. Thank you.
Right. Thank you guys so much for being here. You've been a brilliant audience. Thank you so much to our speakers who have made this event happen. And see you guys for another event later then. Yeah. Bye-bye. Have a good evening.
Thanks, guys, for organizing this event. Thank you.
Thank you.
Bye.